Hey, what's up everybody? This is Ray and welcome back to our beginner OpenGL and GLKit video tutorial series. In this part of the series, you're finally going to learn how to take that 2D square you're working with and move it all the way to 3D using the power of a sequence of 3D transformations. Here's what the app will look like when you're done with this part of the series. In this part of the series, you're going to use the second part of the GLKit library, which is GLKMath. Remember that GLKMath is a set of handy math routines to deal with vector math, matrix math, and so on. The reason I love GLKit is it makes it easy to get started with OpenGL even if you're not an expert on linear algebra. If you do know a lot about linear algebra, great, your life will be easier. But even if you don't, you can use GLKit to think of matrix math as kind of a black box perspective. You can think of it just like other functions that you use in iOS. You don't know necessarily how they're doing what they do, but you know what they do, so you can go ahead and call them. We can think of matrices as the same way. As long as we understand what they do, in other words, they help us move something from one spot of the screen to another, or they help us rotate things, we don't need to necessarily understand the underlying math. We can just use these libraries to do the math for us, since it's a solved problem. So in the rest of this video, we're going to think of the math routines as kind of black boxes that you can use to accomplish the effects you're trying to go for. You can think of a matrix as something that you use to transform the vertices that make up your model. And you can use it to transform those points to a new position, or to rotate all those points, or to scale those points. For example, here's a diagram that shows you how you can use different kinds of matrices on all of the vertices in the RW logo to either translate it, rotate it, or scale the entire model. Now you can create these matrices very easily with GLKit just through single function calls like the one you see here. Once you have a matrix, you can multiply it by a point, represented as a vector, to get a new orientation. So here's an example of multiplying a rotation matrix by a vector to get as a result a rotated vector. The example on the left shows what happens if you rotate first and then translate. The example on the right shows what happens if you translate first and then rotate. Very different results, huh? Which one you want depends on the effect you're trying to get. But how do you control which happens first when it comes to multiplying matrices of vectors? Well, let's take a look. Let's take a look at what would happen if you multiplied a translation matrix by a rotation matrix by all the points in the model. In other words, we're trying to figure out which of these would happen first. Well, it turns out that matrix multiplication is associative. That means you can draw parentheses around any part of the multiplication and do that part first. No matter where you draw the parentheses, you should get the same result in the end. So to see what happens, let's start by drawing parentheses around the final part of this multiplication here, which is the rotation matrix times the vector. So if we do that, we get a rotated version of the logo. So then we multiply the translation matrix by the rotated version of the logo to get an end result, which is something that's been rotated and then translated. Notice that that does not equal the same result as if we were to have translated it first and then rotated that, because it would have rotated around that center point and we would have it up in the air a little bit. If you wanted that opposite result, you would simply swap the order of the rotation matrix and the translation matrix. So in other words, the one on the right is the one that's applied first. Let's dive into matrices a little further. So the size of the matrix that you need to perform a translation depends on the size of the vector that you're working with. And in 3D games, you're usually working with a 4-component vector. Why 4 components? Well, obviously there's X, Y, and Z, and there's one more special component called W, which is set to 1 usually. And why is this? Well, there's 2 reasons for it. First of all, in order to represent a translation matrix, you actually need a 4x4 matrix. So that's one reason. A second reason is you need the special coordinate to perform the perspective transformation, which you'll learn more about later. So for now, all you need to know is that it's actually going to be 4 components, not 3, and the last one's going to be set to 1. So since we have a 4-component vector, our matrix is going to be 4x4, because you need a 4x4 matrix to translate a 4-component vector. And you can think of a matrix as just a 16-component array laid out in memory, as you can see here. All right, at this point we have an array of 16 values in memory. But how do we think of that array of 16 values in terms of rows and columns? Well, there are actually 2 ways we can think about this. We can either think of them as row major or column major. The difference is row major is what you might expect. The first 4 values be row 1, the second 4 values be row 2, etc. But column major means the first 4 values be column 1, and the first 4 values are column 2, and so on. And this is actually the way that GLKit uses. So this array that you see here, if you drew it out as a 4x4 matrix, it would look something like this. Notice that M00 down to M03 is column 1, and those are the first 4 values in the array, and M10 through M13 are the second column, and those are the next 4 values in the array, and so on. Now, the reason GLKit uses column major matrices like this is because when you have a column major matrix, you can post-multiply the points by that, and so that's what we'll be using for the rest of this workshop. If you were using row major matrices, you would have to take the points first and then multiply them by the matrix instead. Again, the great thing about GLK math is you don't necessarily need to understand any of this. You can just treat the functions as black boxes. But the reason I'm including the information on column major versus row major, etc., is that as you dig a little bit deeper into GLKit, if you're studying up on some linear algebra, you'll remember this and have this to go back on in the future. All right, believe it or not, that's all you need to know in order to start doing the transformations to start taking your scene from 2D to 3D. And there's 4 different transformations that you need to use in order to make this happen. The first is the model transformation. So this is usually you have your coordinates for your model in what's called local coordinates. For example, if you were using a 3D modeling program, a lot of times your object will be centered at 0, 0, and all the rest of the points will just go out from that. But of course, you don't want every object in your game to be at 0, 0. You're going to have some here, some there, and so on. So you need a matrix to say, where is this object in the world? How is it rotated? How is it scaled? That's called the model transformation. The next transformation is called the view transformation. So at this point, you have everything nicely put in different spots in your world, but you might be looking at your world from a different perspective. For example, I might be standing over here looking this way, or I might stand over here and look that way. The next is the projection transformation, and this kind of has a dual purpose. The first purpose is to make things up front look bigger and things further away look smaller. You can think of this, the classic example is a train track, where if you're standing on a train track looking down, the train track looks a lot bigger closer up to you and a lot smaller further away. So the second purpose of a projection transformation is to convert the area within inside a certain box in front of you, like think of a cone that's chopped off at 2 spots. That box is going to be mapped to the normalized coordinates, which is the 2x2 cube centered on 0, 0 that we've been working with in this workshop. And then finally, there's the last is the viewport transformation. It takes that normalized coordinates and maps it to the pixels on the screen. And we've actually already been working with this. That's actually done for us behind the scenes since we're using GLK View. So let's go through each of these transforms step by step and see our scene transition bit by bit as we add each of these transformations into a 3D scene. Again, the first transform is called the model transform, and that's what takes the local coordinates and maps them to where it is in the world. So what we're going to do is we're going to add a couple properties on our model object for position, translation, and scale. And then we'll use the GLK math routines like you see here to generate a matrix for each of these different types of transforms. Finally, we'll multiply all of these different transforms together into a final transform, which is a combination of these 3 called the model transform. Let's take a deeper look of the overall strategy of how this is going to play out in code. So there's 3 players here. There's first of all RWTModel, which is remember the class that represents your model. Right now it represents our square, but we're going to have different subclasses for this later. Then we have RWTBaseEffect. This is the class for this shader. And finally we have the Vertex shader itself. Like I said, we're going to have some new properties on RWTModel for position, rotation, and scale, and we'll set those at some point. And then when we go to render the model, the RWTModel will have a method to take the position, rotation, and scale and use those GLK math routines to generate a matrix for each of those and multiply them all together, and in the end get a final model matrix that represents the combination of those 3 different transforms. Then we will pass that model view matrix to RWTBaseEffect and call it prepare to draw. Now finally, RWTBaseEffect needs to send that model matrix to the shader. Up to this point, the only way you've sent data to the shader is as vertex attributes, which means you have different data for each vertex that you're drawing. But in this case, we want to use the same model matrix for every vertex that we want to draw. So it would be pointless to duplicate this information over and over again. Well, there's another type of input parameter you can use called a uniform. And as you might expect, that's useful for when you have data that's going to be the same across all vertices, and that's perfect to use here. So let's take a look into this a little bit further. So here's the example of what we're going to do for RWTModel. We're going to have a whole bunch of new properties here for position, rotation, and scale. And then here's our helper function to create a model matrix. So we're going to initialize the model matrix with a special value called GLKmatrix for identity. This is a matrix that if you multiply it by a vector, it does nothing. It makes no changes to it. You get out what you get in. So it's like a good starting point. And then we're going to multiply that starting matrix by several other matrices representing each transformation. So the first is GLKmatrix for translate, and it will do two things. It will generate a translation matrix based on the values we pass in here, x, y, and z, and it will take that matrix and multiply it by the matrix that we have passed in, which right now is identity. And going on to the next line, if we call GLKmatrix for rotate, it rotates around the x-axis 1, 0, 0 by rotation x, and takes that resulting rotation matrix and multiplies it by the previous model matrix, which right now at this point is including the transform. And then we just repeat these steps for the other two rotations and for the scale. And in the end, we have a matrix that represents the combination of all of these effects, which is our model matrix. So in render, we simply set the model matrix to the combined matrix that we generate here. Now note, which of these do you think occurs first? Do you think the translation occurs first, or do you think the scale occurs first? Well, the answer is that the scale occurs first, because remember back from our diagram, because we're using column major matrices and we're post-multiplying, the one on the far right is what happens first. So scale happens, then rotation, then translation. Moving on to RWTBaseEffect, we have a new property here for the model view matrix that we're going to add, and now we need to send that to the Vertex shader. So what we did for the Vertex attributes is we told, before we linked the program, we told the Vertex shader what index it should use for each Vertex attribute. For uniforms, we're actually going to do the opposite. We're going to let the program link and choose anything for where it puts the uniforms, but then after the fact, we're going to ask it where did it map each uniform, and we'll get the index back, and we'll store it in model view matrix uniform. And then before prepare to draw, we have to set that uniform, and the way we do it is GL uniform matrix, and then it has a couple different methods you can use based on the data you're passing in. We're passing in a 4 by 4 float matrix, so we put 4FV for 4 float values. And then we pass in the index and the matrix itself. And you can get the matrix itself by, if you're using GLKmatrix.m will give you the raw data. Last but not least, the Vertex shader, we're going to add in a new input variable for that uniform. Notice we have to use the uniform keyword. And then for GL position, we're going to pre-multiply the position by that uniform matrix. So let's see how this looks. We have our project here where we left it off last time, where we have our colored square to the screen. And we're going to start by adding a model transformation. So we can move this model from being centered at 0, 0 to maybe moving down a little bit. So let's go ahead, and we're going to start the opposite way from the slides. We're going to start by adding a new parameter here to our Vertex shader. So to do that, we just say uniform, because we want it to be the same across all vertices, and we'll give it high precision here, and we'll make it a 4 by 4 matrix, and we'll call it UModel View Matrix. And then, rather than just setting the final position of the vertex to the input position, we will transform that position by multiplying it by the model view matrix. Okay, great. Now what we need to do is modify RWTBaseEffect to take a parameter for that model view matrix. Notice to get the GLKmatrix 4, I need to bring in GLKit, and we can do that with the new import command. Switching to RWTBaseEffect.m, I'm going to go ahead and add in a new variable here to store the location of this model view matrix uniform. And then we scroll down here to the compile shader method, and after we link, notice it has to be after, we need to get the location of that. So we're going to say model view matrix uniform, and then we're going to do GL get uniform location. We give it the program handle, and we give it the name that we put in, which we put in UModel View Matrix. We'll also initialize the model view matrix to a default value here, which will be just the identity matrix since we don't want any changes unless we actually modify this. Finally, in prepare to draw, after we call GLUseProgram, we want to set the uniform value. So you can do that with GLUniform matrix. I notice there's a bunch of different versions here, but we want the one that has 4 float values. And we pass in the model view matrix uniform, the number of matrices to pass, which will be 1, whether or not to transpose, which we don't want to transpose that matrix, and then self.modelViewMatrix.m to get the raw data to send across. So now, if someone sets this model view matrix property on RWTBaseEffect, it will be passed to the shader before it's rendered. So the last thing we have to do is actually create the model view matrix and send it to the RWTBaseEffect. And that's going to take place in RWTModel. So here I'm going to add a few new properties for all of the things that we want to be able to translate and scale and so on. Now down here at the end of this file, I'm going to go ahead and add in the model matrix method that you saw from the slides. Notice here that there's a couple different ways that we can do the translation. We can either call GLKmatrix for translate, which lets us create a translation matrix by passing in these 3 values and multiplying the resulting translation matrix by another matrix, sort of. So we create and multiply in one. Alternatively, we could say GLK matrix for make translation, which would just do the step of making the matrix, and then we'd have to multiply the matrix by the result. But we want to combine the two, so I'm just going to use that option. For the GLK matrix for rotate, you give it an axis about which to rotate. So we're going to do 1, 0, 0 for the x-axis, and then we'll just change that for the different axes. For the scale, we're actually going to use the same scale for x, y, and z, but sometimes you want to have a different amount it's scaled along the x than along the y, so you can kind of stretch the model. And in fact, you'll be doing that in one of the challenges, but for now we just want the same scale applied evenly across. So then all we have to do is in render, we have to send that matrix across in the model view matrix parameter here. Okay, there's one last thing I need to do. We need to initialize all these properties with some default values here. And last but not least, let's try out what we have so far. I'm going to go to RWTViewController.m where I'm setting up the scene, and let's set the square to be an initial position. Square.position, build and run. And notice how it is now translated to be down a little bit and over to the right a little bit, just by setting the square's position. To let you better see that we have control over this, let's make this animated. So I'm going to comment this for a minute. To make this animated, GLKViewController has a method that's called each frame called update. All you have to do is override it like you see here. So what we're going to do is we're going to add a new method to RWTModel called update with delta. And in RWTModel.m, we'll just initialize this with an empty implementation. But actually in RWSquare, we'll have some custom code to make the square kind of translate back and forth. So we want it to, every 2 seconds, move back and forth. To do that, we add the following line. Okay, so what we did here is the sine function, as you know, it goes between 1 and -1 over a period of 2 pi by default. But if you multiply the result by 2 pi and divide by something you want, you can switch to another period instead. So that's what we're doing to make it go. Oh, and I should set this to every 2 seconds. That's what it's making it go every 2 seconds instead of 2 pi by default. So that's changing the x between -1 and 1 every 2 seconds. And then we don't want it to change the position.y or z, so we'll just pass in the original values there. So now we have this new update with delta routine. So we'll just go here in the RWT view controller and the update method that's called automatically, and we'll just say square update with delta, and we'll pass in time since last update there. And I should probably, time since last update is a ns time interval. So let's go ahead and modify the parameter here to be correctly an ns time interval instead of a float. So now if I run, check it out. We got our box swinging back and forth with the power of model matrix. At this point, we have our objects in various places on the world based on the properties that we set up on them, such as position, rotation, and scale. But even though they might be at different spots in the world, we might want to look at that world from different perspectives. There's actually 2 different ways we can think about this. We can think of taking the world and shifting the world off to a different position, or we can think of taking the camera and shifting the camera off to a different position. They're actually both the same thing. It's how you think of it. And for this workshop, we're going to think of it as moving everything in the world to a different position so we can see it from a different angle rather than moving the camera. But you can write your code in both ways. It's really what's most convenient for you. Let's take a look at how this looks in code. So moving on to RWTModel.m, we're going to take a new parameter to the render method, which is the parent model view matrix. This will represent that a parent object can contain multiple child objects. So our parent object so far is going to be the scene itself. And the scene has many models that it's probably trying to draw. So you can set the parent model view matrix to be however much the scene has moved. And then as the scene moves, obviously everything that's a child of the scene should move with it. So what you do here is you multiply the parent model view matrix by the model matrix. In other words, the model matrix is applied first, and then the parent model view matrix, which in this case is going to be the view, is applied second. And now we have a combined model view matrix. So moving to RWTViewController.m, we're going to set the view matrix here to be a translation of 0, -1, 0. So you can think of it in 2 ways. You can think of it as moving everything in the scene down 1, or you can think of it as moving the camera up 1. At this point, we have our box moving back and forth using a model matrix. But what if we want to move the entire camera up a little bit, which would make everything appear to move down? Well, we can do that. So like we talked about, what I want to do here is modify this render method to take a parent model view matrix. And what we'll do is we'll calculate the final model view matrix by multiplying the parent model view matrix with this object's model matrix. Now all we have to do is switch to RWTViewController.m, and before we render here, we're going to create a view matrix. So we can make a translation matrix with GLK matrix 4, and we want the make translation option because that doesn't multiply an existing matrix, it just makes a matrix. So we want 0, -1, 0. That moves everything on the screen down 1, and then we'll pass in that as the view matrix. Now that's really it, because we're leveraging all the code we've already done. So we're multiplying this view matrix by the squares model matrix to get a model view matrix, which is then passed eventually to the shader. So if I run that, now we have the square moving again, but we're looking at this scene from a different perspective. The third transformation is the projection transformation. And this is the one that takes the camera coordinates and eventually gets them into normalized coordinates. It also does the thing where things that are closer up are bigger and things that are further away are smaller. So we're not going to cover the math behind this, but we will say that there's a routine that you can call in GLK math to generate a projection matrix, and it takes several parameters. And what it's doing is, you can imagine it as defining a pyramid coming out from your eyeball looking ahead, except there's a certain area that's chopped off in front, and anything before that point you won't see. And there's a part in the back that's chopped off, and anything further away from that you can't see. But anything inside that area is something that will be visible to the screen and mapped to be that normalized device coordinates. It will also make it so that the things closer up are bigger and things that are further away are smaller. So the parameters that you can set here are, first of all, the field of view, the angle between the top and bottom of this cone, and also the area, how far up is the near plane and how far back is the far plane. And what it's basically doing is it's drawing a bunch of rays, you can think of it, out of your eye to look at the objects in your scene. And wherever it intersects that front plane, there's going to be a pixel drawn there. So it's basically taking a 3D world and projecting it onto a 2D plane, which is your screen. Let's take a look at the overall strategy for how this projection transform is going to work. So this time there's 4 players. There's the RWT view controller, the model class, the base effect, which is the class representing the shader, and then the shader itself. So the view controller is going to generate the projection matrix and pass it over to the RWTBaseEffect. Why? Because we want to use the same projection matrix for everything in the scene. Next, when we render a model, it will always call prepare to draw on the base effect. And what the base effect will do is pass that projection matrix onto the vertex shader. So now the vertex shader has 2 uniforms. One is the projection matrix and one is the model view matrix.
Okay, so we have our box moving back and forth. Now, you might have noticed something that's been maybe bothering you the entire time in this series so far, and that's that we've made a square that's supposed to be a 2x2 square, but the problem is it's more looking like a rectangle. That's because the coordinates are we're still in the normalized coordinates here, and it's making it stretched based on the aspect ratio of the viewport here. But if we're making a 2x2 square, we want it to look like a square, and so that's one of the things that this projection matrix will fix for us, as well as enabling full 3D. So what we need to do here is, first thing we need to do is we're going to actually modify our vertex shader. We already have a uniform for the model view matrix, so let's add another one for the projection matrix. And what we'll do is we'll just multiply the projection matrix by everything else. Now, we could have pre-multiplied the projection matrix and the model matrix and sent that as a single parameter rather than having to do the multiplication here. But the reason we've split this out into 2 different uniforms rather than pre-multiplying them like we did for the model view matrix is that later on when we do some lighting, it will be helpful to have the projection matrix as a separate uniform. So that's why we're keeping that separate right now. Okay, so now that we've added a different uniform, we need to modify our base effect for this. So first we need to add a new projection matrix property. We need to create a location to store this. And down here, we should set the uniform to, we should get the location of the uniform. And last but not least, we should send it through and prepare to draw. Okay, that's that. We don't actually have to make any changes to the model class because it's going to be the view controller that will set the projection matrix. So going back to the viewcontroller.m, in setup scene, here's where we will set up the projection matrix. To create a projection matrix, you just use GLK math routine, GLK matrix for make perspective. And you pass in the field of view in radians. And I don't usually like to think of things in radians, I like to think of things in degrees. So GLK math also has a helper function for that. It's degrees to radians. And a typical value to use for field of view is 85. So you can use that or you can tweak it to whatever you like. And then for the aspect ratio, you're looking for the width divided by the height of wherever you're rendering to. And we're rendering to self.view, so we can get it from that. For near Z and far Z, we're just going to set 1 unit ahead and 150 is the range. So anything between 1 and 150 away from the camera will be visible. Well, this leads us to a problem right here because the model is at 0, 0, and so it wouldn't be visible right now. But I'm going to shift this to -5 so it basically moves back so it's within the that pyramid that comes out from the camera. And I run, and there we go. Now it actually looks like a square, and it's moving back and forth.
The fourth and final transform is the viewport transformation. And that's what takes that normalized coordinates, that 2x2 cube centered on 0, 0, and maps them to the pixels on the screen. And actually, this is done for you automatically already because you're using GLK View. Behind the scenes, it's calling a method like this, GL Viewport, passing in the width and height of the screen, so it knows how to do that mapping. And of course, it's factoring in things like are you using a retina display, etc. But so you don't need to actually do anything to make this work, but I wanted you to understand that it is there. Okay, we've covered a lot of important concepts here, so I want to make sure everybody's following along. So we're going to have a pop quiz. As always, I'll go through, go ahead, write down your answers, pause the video, and then play again and see if you got them right. So first of all, what is a model matrix? What is a view matrix? What is a projection matrix? And what is a viewport matrix? Finally, which matrix is multiplied by a position or vector first? Okay, so the answers are a model matrix. This is the one that takes the local coordinates and gets them into the world coordinates. What is a view matrix? This is the one that takes the world coordinates and gets them into camera coordinates. What is the projection matrix? This is the one that takes the camera coordinates and gets them into normalized coordinates. And finally, the viewport matrix takes the normalized coordinates and gets them into Windows coordinates. The one that is applied first, remember, it's the one on the rightmost that's going to be applied first, and that's going to be the model, followed by the view, followed by the projection, last but not least, the viewport. Believe it or not, our app at this point is already fully 3D and has full 3D support. So although we're rendering a square right now, we can easily extend this to render a cube instead. We just need to add more vertices and more triangles. So we already have part of a cube. We have the first 4 vertices in the cube, that's sort of the front part. We'll add another 4 that represent the back part. And then after that, we just have to add a bunch more triangles. So right now we have 2 triangles for the front face, but we also need to do the back face, the left and right, and the bottom and top. So here's what this would look like. As you can see here, we already had the coordinates for our front face. So we'll just repeat those down here for the back face, and we'll put -1 for each of the z coordinates instead of 1. Down here on our indices, we already added the 2 triangles for the front face. So we'll just add 2 more triangles for the back face. For example, 4, 5, 6 is triangle number 1, and 6, 7, 4 is triangle number 2.
Okay, so we have our 2D square here. Let's move this to a 3D cube. This is one of the nice things about the way we have our code architected right now. To make a square, we make a square class that derives from the model, and then we have our vertices and indices for this square here. So we're going to, instead of modifying this, we're just going to create another subclass of RWTModel for a cube instead. So I'm going to create a new file here, iOS Cocoa Touch Objective-C class. We'll call it RWTCube, and it's going to derive from RWTModel. Switching to RWTCube.h, let's create an initializer here. Switching over to RWTCube.m, the first thing I need to do is import the vertices and the indices. Now, rather than me typing this all out, I've already figured this out, so I'm just going to paste them in. You've seen these. These are from the slides. They match up exactly to the numbered vertices on the cube. And you've seen these two. This is the front face triangles, the back face triangles. And here I've just pasted in the rest of the triangles for the left, right, top, and bottom. If you're curious, you can pause the video and maybe try to figure this out on your own. It's a good learning experience. Now that we have the vertices, we can implement the initializer, and it's actually very similar to this initializer, so I'm just going to take that bit of code there and paste it. The only difference is, since we named the vertices and indices the same, the only difference really is the name of that right there. Let's see. We capitalized V and I, though, so I'll just lowercase it here. Okay, next we're going to, for fun, make this thing rotate and update with delta. So we'll do that just by saying self.rotation z plus equals m pi times a delta. So in other words, m pi would mean it's rotating a certain amount each frame, minus dt. Now that we have this new class, all we have to do is go to RWT View Controller, import the new class, and then just add lines similar to adding in the cube to make this thing render out. So if I run this, hey, we have a cube. Now, it's not rendering quite right now. There's some weird stuff going on. So let's discuss what's going on here.
As you can see, our cube looks kind of messed up right now. What's going on is sometimes it's drawing a pixel from a back face of the cube in front of a pixel of the front face of the cube. But obviously we don't want that to happen. We want the ones that are in front to show up on top of the ones that are behind. So how do we fix this? Well, one way to fix this is through something called depth testing. And to understand this, you have to remember back to the way beginning of this workshop where I talked about something called frame buffers. Remember, a frame buffer is a collection of buffers, and one of them is a color buffer. The color buffer is the buffer of pixels that you draw to that GLKView then presents to the screen. And I said that there are several other buffers and they have question marks there that you can configure optionally. And one of these things you configure optionally is a depth buffer. And this is actually really easy to set up with GLKit. It's literally like 2 lines of code to get this to set up and work. And once you add those 2 lines of code, what it does is whenever you go to draw a pixel, not only does it draw it to the color buffer, but it also stores in a separate buffer, the depth buffer, the Z value of what it just drew. So then when you go to draw another pixel, it says, okay, I'm about to draw this pixel. I'm going to check the depth buffer first and see if there's anything in there that's supposed to be in front of this pixel that I'm drawing. If there's something in front of it, you don't want to have something that's supposed to be behind come up on something in front. So you just don't draw that pixel in that case. And that way you make sure that you're always having the things that are in front show up first. However, depth testing is not the most optimal way to solve this problem. There's a better way called backface culling. The reason why depth testing isn't perfect is because you're kind of wasting some processing if you think about it. So you know that the back face of a cube, if you're looking at a cube and whatever's the back of it, you never want to draw any of it because the other faces are all going to be covering that. So if you're using depth testing and not backface culling, you're going through your fragment shader on every single pixel inside that back face and it's saying, nope, shouldn't draw this, shouldn't draw this, shouldn't draw this, basically wasting a lot of time. Whereas if you just ignore drawing that face completely because you know it's going to be covered, you wouldn't have to process it. And the way backface culling works is all you have to do is specify the triangles of your geometry a certain way. You have to specify them in counterclockwise order from the viewer. So once you do that, it will automatically not call anything that shouldn't be rendered. The great thing about backface culling is if you're using a 3D modeling tool like Blender or 3D Studio Max, it will automatically generate your vertices in the proper order. But if you're doing it manually, it can be sometimes a little bit tricky to get this right. So I just kind of think through the proper order to do for the cube here. And the way I figured this out is just by sketching it out on paper. So I just wanted to include here what I did to sketch this out in case it's useful to you and you want to figure this out on your own. And the way I thought of this is I imagined like the front face is obvious, right, to get the order right. But to get the back face's order, I imagined myself walking around to the back of the cube as if I was back there looking at it. And what would the proper order be looking at it that way? Which would be the front and which would be the back?
So we have our messed up looking cube here. Let's solve this in both of the different ways that I mentioned back in the slides. So the first way is with depth testing. Even though it's not the most efficient, it will work. So to enable depth testing, there's a couple things you need to do. First, on your GLKView, there's a parameter that you set here called drawable depth format. By setting this to something, you're telling GLKit to set up one of those depth buffers for you. So we're going to set it to drawable depth format 16, so it sets up a depth buffer. Next, down here, when you're drawing, you want to clear 2 different buffers now. You want to clear the color buffer and you OR that with the depth buffer, so both are cleared. Next, you have to enable depth testing with GL depth test. And that's really it. Then when you run, it is making sure that the things in front are drawn on top of the things that are behind. So let me show you the second way to fix this. First of all, I'm going to comment out the depth test for now to prove that it's broken again. And let's solve it the better way. And this is just a one-liner. GL enable GL cull face. That enables backface culling. Now it works as before. And the reason this works is because I was very careful when specifying the vertices in that cube to put each of the triangles in counterclockwise order so that OpenGL knows whether a face is facing backwards or facing forwards. But in a real app, usually you want to have both of these. So cull face takes care of the own object, depth test takes care of objects drawn on top of other objects. So I'm going to have both of them enabled, and everything looks great.
Alright, that's it for this video tutorial, and as always we like to leave you off with a challenge. I think you'll really enjoy the challenge this time. If you only take the time to do one challenge in any of the videos, I really recommend you do this one. It'll be a great learning experience and a lot of fun. What you're going to do is you're going to create your own 3D geometry for a cone. And then you'll use some transformations to shrink and stretch that cone so it looks like a rocket ship. Then you'll add some code to make that rocket ship blast off into space. And finally, for the Uber hackers out there, you'll make the camera track the position of the rocket as it blasts off into space, and you'll even add a screen shake using some transformations. So I hope you enjoyed this video tutorial. Thanks for watching, and we'll see you next time.